Okay, this is page 126 of your resource package, question 19 MCQ. This is for electromagnetism. Okay, the diagram shows a flat surface with lines OX and OY at right angles to each other. In order to produce a magnetic field at O, which is over here, in the direction of OX, that means at O, I must have a magnetic field with the direction parallel to OX. Alright, where should I place a current carrying straight conductor so that the direction of the current plus the conductor will give me a magnetic field direction that is shown in green. Okay, but as you know, for a straight wire conductor, it is usually circular for the magnetic field. Correct? That means I'm looking for this portion. Not this because it's pointing in the opposite direction. Not this because it is supposed to be pointing in the direction of OX. That is how you should interpret the question. Right? So for straight wire, what do you all use? Fleming left hand or right hand grip? Right hand grip. So I need the current to be going into the page and my finger to be placed like that. Obviously, I can't draw it inside lah. Okay, so you all follow Yes. If it's out, then there's no way that we can put it at Q and P. Okay, how about I draw the magnetic field if the wire is placed at P. I draw at P, and let's say I choose the current to be going in, can? Right? So the cross shows that the current is going in. Then, if I were to put my thumb facing in that direction, correct? So, if I have a current at P, the magnetic field direction will not be parallel to OX. Correct? It will be either up or down. It will not be parallel. Correct? Look at this part. If I continue drawing at O, what will the direction of the magnetic field be? Up. But I want to the right, OX. Can you all see that? But of course here, it will be to the right. But it is not at O. I need it to be at O. Huh? At where? So now I show the correct answer. Now. So if I have a current carrying conductor at P, it will either be up or down depending on the direction. It will never be left or right. Never. Correct? If I were to draw out the magnetic field in a circular manner, and it will be in a circular manner. So now I'm going to do the correct answer. So this is O. I need it to be in this direction. So now I try Q. Q, I also let the current to go in. I'm just trying, I'm guessing and check. So if the current is at Q, is going in, we use our right hand grip rule. Let's draw our first magnetic field lines. Agree? Clockwise. Hey, got chance. If I draw it at O, isn't it in that direction? Yeah. So answer, position of the conductor is at Q and the direction of current is into the plane. So answer is C. Okay, the next question that we're going to go through is Anderson, page 17, question 9 and 10. Figure 9.1 shows part of a toy which contains two ring-shaped magnets. They are permanent magnets. I don't know whether it's important, but I mark it out first. Plastic rod passes through the center, and the top magnet can move up and down freely above the plastic, around the plastic rod. Magnetic poles on the bottom magnet are shown. Okay, top magnet floats mark the poles. So here definitely no. Why? Opposite, repel. This one very simple. Like that, 2 marks. Simple. Yes? Move on. The top magnet is replaced with a ring made of iron. Explain why the iron ring sticks to the magnetic material. It will be it will undergo magnetic induction with the bottom facing the magnet to be induced with a south pole. Okay, and since unlike oh sorry, light poles. Hey, I heard somebody say opposite. Okay, so anyway, capture on video. Never mind. People make this. Okay, page 17, question 10, same school, Anderson. It shows a simple DC motor. Motor is connected to a battery with a positive terminal connected to A. So when they tell us that, we can draw in the direction of the current. Okay, explain why the coil turns in the direction shown. Did they give us the direction of turning? Clockwise or anti-clockwise? Anti-clockwise. So what do you need to do? Revise this again. Drawing of this diagram in a 2D perspective. North, south, A, B. B is dot or cross? A is cross. This was provided by this. They give us the direction of current. Then we have to work out what is the direction of the force on B. So what do we use? Fleming left hand rule. So this one should go up. This one should come down. So in your answer, you say we use Fleming left hand rule. Okay? The thumb, how many marks is this? So you have to write a lot. You can just say, because I use Fleming left hand rule, give me my 3 marks. Impossible. So the thumb represents a force. First finger represents magnetic field. Middle represents current. Then you have to choose either A or B. If we use A, then you say the force on A is down. The force on A is down by using Fleming left hand. But you cannot just say by using Fleming. It's 3 marks. So you need to talk about what each finger represents. Okay? Then after that, if A, the force is down, B, you don't have to go through everything again because you have already explained previously. Yes? So you just say B because the direction of current is opposite. The force on B is up. Right? Therefore, it will then turn in a anti-clockwise direction. Are we okay? You all know how to answer. Look at the number of marks and answer accordingly. But if the question say, what do you use to determine the direction of the turning? 1 mark. You just say by using Fleming left hand rule. Which law, which rule did you use? Okay, can Fleming left hand. Now, state 2 ways which can cause the turning effect on the coil to increase. Increase current, what else? Number of turns of the coil. Okay, this is the third time we see this. Number of turns of the coil. I tell you, all the question repeats. They will repeat. I will give you all last year's prelim. Most likely, whatever came out in last year's prelim will not be tested in this year's prelim. It shows a setup to investigate how a doorbell works. A chime bar and a magnet are suspended with chain. Okay, so we take note that this is actually an electromagnet. And if this is positive, this is negative, current will come out. Now, what is important here? I need to mark out the direction of the current. So the direction of current is, agree, this step is extremely important. With this, you will apply right hand grip rule for solenoid. Okay? Now, when you apply right hand grip rule, you need the direction of this current there. So if I do this, my north is facing the thumb, my south is over here. So this will be my south and this will be my north. And south, they will repel and this thing will come here and they will hit the copper chime. So let's see, explain why the magnet moves towards the iron core when the switch is open. When the switch is open, so I am jumping too fast. When the switch is open, is there any current? No current, no magnetic field, right? So this was in the previous question. Iron core is magnetic. When the switch is open, there's no current. No current is a magnetic material. It will be magnetically induced with a north pole that on the side that is facing the south pole of the magnet. South pole of the magnet is here. Where's the side that faces it? Over here. So magnetically, it will be induced with a north pole. So if here is north, here will be south. Opposite will then attract, right? Opposite attract. Therefore, it will move towards the iron core. Okay? Then this part explain why the magnet hits the copper chime bar when the switch is closed. So do you know how to answer? When switch is closed, so when the switch is closed, there will be current flowing. When current flow, it will produce a magnetic field in the solenoid, right? And when we apply right hand grip rule for solenoid, the end that faces the south pole of the magnet, which is here, will then become a south pole. That's why it will be repelled because light poles repel. Okay? 2 marks. I know expecting you all to write a lot, but now I'm just including all the concepts. Okay? So then you'll be repelled, then it will hit the copper chime bar. Okay or not? Part 3. The battery connected to the iron core is replaced with a low frequency alternating current supply. What does it mean? This is DC. Current always comes out from positive. If AC, the symbol, look here, the symbol looks like this. Like that, this is AC. So it will take turn having current come out from here, this way. Once current come out, go back, the current will go the other way. This is called alternating current. Not a loop, just that. Here becomes positive, then here becomes negative. Then the next cycle, here becomes negative, here becomes positive. It's a cycle. Real example. All these are AC. But because we didn't do the last part of the pure chapter, you all didn't know about this. So AC is all this. That means the current keeps changing direction. But anyway, not in our syllabus. But now they can just tell you that alternating current, the current changes direction. So if the current changes direction, what is the implication? The direction of the magnetic field will change direction as well. So right hand grip rule, 1 minute or 1 second you are doing this, the other cycle you are doing this. This north, south, north, south. So do we need iron core or can we do with a steel core? We need iron because it needs to be magnetized and demagnetized north, south, north, south, north, south. You all get it? Huh? When we replace it with AC, what happens to the direction of current? It keeps changing, right? What happens to the magnetic field's direction that it produces? It keeps changing. So what happens to the poles here? It either becomes south or north or south, keeps changing. So it keeps getting attracted, keeps getting repelled. This is fixed. This north and south of the magnet is fixed. But here, when it becomes north, it will go towards them. When it becomes south, it will go away. So it will keep heating and not hitting the copper chime bar. If it gets attracted, it will not hit the chime bar. If it gets repelled, it will hit. Heat don't hit, heat don't hit. That's why it will keep ringing. Okay, the current keeps changing direction. Are you all listening? First, it keeps changing the direction of the magnetic field direction in the solenoid. Thus, therefore, the poles induced on the iron rod keeps alternating, right? Thereby attracting and repelling the permanent magnet. So that's why it will keep hitting and not hitting the copper chime. Yes, question. Again, these arrows are very important. Draw the arrows. Alright, draw the direction of the arrows on the wire that's facing you. Behind you, you are unable to draw. Draw the one that's facing you. So over here is like that. Now, is here side P, is it north or south? It is south. We do the same for here. It will be north. So, one mark like that. And explain why it will experience a force. Experience a force. What is the keyword here? Okay, it's due to the interaction between the magnetic fields of the current carrying wire and the external magnet. Okay, one mark, just like that. So there must be interaction. Now state the direction of the force experienced by the current carrying wire. What do we use here? Fleming left hand. So external magnet is like that, north to south, yes? External magnet goes from north to south. What is the direction of the current? Current is used using, represented by middle finger is pointing down, but this is north to south, so it will be into page. Into the page, out of the page, into the page. Okay? So this one will be into the page. Right? Suggest one method to increase the strength. This one you all should know. Okay? So how do we increase the strength of the force, stronger current or stronger external magnetic field by increasing the voltage of the battery? Alright, let's go to the next question. Page 59 CHIJ paper, it shows a piece of recording tape passing under the recording head of a tape recorder. There's a current passing through the coil. When current flows, it produces a magnetic field. The tape is coated with a magnetic material. What is this? Okay, why is the tape magnetized in opposite direction? Because the direction of the current in the coil switches or change, right? Now the tape is moved faster. State how this changes the pattern on the tape. How? What happens to the pattern? The tape is moved faster past the recording head. Okay, so if it's move faster, more sections of the magnetic field pattern will be facing the same direction. Correct? Or because my current didn't change direction so many times, but it passes through like that. Alright. Okay, part 4 shows the cross-section view of the coil. So this cross-section view, and being a coil, it will be a solenoid. It will be a solenoid. So you have to use your right hand grip rule for solenoid. What? Referring to the key. Referring to the key. Plus is to represent direction of what? Direction of what? Current. Minus is out of page for the direction of current. So how should we grab using our right hand grip rule? Okay, so basically you need to use right hand grip rule for solenoid. Based on the direction of current, your hand should be grabbing it this way. Yes, and my thumb is facing to the left, so my knob is there. But you don't just label north and south. You draw the direction of the magnetic field. Okay, always comes out from north and enters the south. Now this one, have we done this before? What is the direction of the current flowing through the coil A, B, C, D? In this case, are they giving us force, current, or external magnetic field direction? Which one is left out? Current. They leave out the direction of current, but they give us a force. So which side do you want to do? As always, if you are not clear, draw the 2D. AB, the force is up. So now, north to south, my thumb must be facing up. Correct? So my middle finger pointing out of the page. That means the current is a dot. Make sure all can do. Don't just sit there. Make sure all can do. You see these questions repeated every year. In every paper, right? So you must know what to do. Calculate the moment. This one moment is force times perpendicular distance. 20 Newton here is how much? Each side is 5 cm. So 2.5. 2.5, right? Caused by these forces. So this one will be 20 times 2.5. This one will be 20 times 2.5. So you add up the moments, each force. You still must do that perpendicular distance to the pivot. Okay? The direction of the current is parallel to the external magnetic field. It must be perpendicular, then there will be a force. Yes, look at Fleming left hand. Are they all forming 90 degrees? But now if my current of direction and my external magnetic field is same direction, it becomes this way. So this is not Fleming left hand. So therefore 0 force. Get this part? But if you memorize, it's just a 1 mark. They are parallel. Now changes were made to the coil. So this one we have done this in our tutorial, and I'm sure some of them actually repeat, right? Our AC also changed direction. Battery is replaced by an electrical source, which produces a current that changes direction 50 times. This is your AC. Right? So the coil will be vibrating like that. 50 times a second. Can any of you change direction 50 times a second? Not possible, right? Not possible. Huh? So imagine this current flows in the coil. It wanted to go clockwise, anti-clockwise, so it will just be vibrating. Right? There will be no real turning. Okay or not? So that's why all our motor are what motor? DC motor. DC motor.